I got started in research actually in an interesting way for me. I did an honours degree at Melbourne Uni in the early 1980s, and that gave me a taste for research in mathematics. I was, at the time, a bonded studentship holder in the Victorian system, which meant my university career had been supported by the Victorian government, and they wanted me to go and teach in country Victoria for a few years, and I had to try and put that off as long as I could. So I got a taste for it. I went and did a Masters by Research at the same time I was doing a Dip Ed, and that really gave me a sense of what I wanted to do and the focus I wanted to have. I did that. Then I went out and taught in schools across Victoria for about 7 or 8 years and decided I did want to get back into an academic career. I actually did some research while I was teaching in various ways. I kept engaged with my discipline and my particular area of interest, and then of course moved into higher education again and went back to do the PhD with the supervisor I had for the Masters some years earlier. So it was great that he was still available and interested and had some great topics, so that got me into it. And at the time I was beginning my academic career at what became the University of Ballarat. So it was a small regional Australian university with not a great history of research strength in any particular area. It was quite good in the environmental sciences and quite had some interesting research capability in human movement, sports science, but certainly not in the mathematical sciences. So it gave me an opportunity to involve myself in research management at the same time. So that really kicked it off. My particular area of interest in mathematics is in optimization. So optimization is a part of mathematics, as the name suggests, that deals with trying to find optimal solutions to quite complex problems. So mathematics is quite often, applied mathematics is quite often about modelling a physical system in some way. If you can come up with a model that's a reasonable approximation to the real world behaviour of a system, then you're able to tweak the model, change the input parameters and various other things to try and find what the optimal solution to the original problem was, or to get the optimal behaviour of the system that you're studying. So optimization deals with these sorts of mathematical models and how to find optimal outcomes. So it has a lot of application in areas like economics, where people are often looking for particular equilibrium points in economic modelling, which are very, very important, in engineering and in various areas of business and industry, where you're looking for maximum or minimum outcomes. You might want to minimise cost, you might want to maximise profit, you might want to minimise use of raw materials in various ways. So you can set up complex mathematical models and then seek out an optimum. Now, that's the broad area. I was particularly interested in a pathological end of the spectrum, so I was interested in what were essentially what we would describe as infinite dimensional models. So they were models that had technically or potentially an infinite number of variables that you could be dealing with in the model. So that made them more complex for those reasons. And I was also dealing with problems where they had a lack of what we described in mathematics as smoothness. So they were essentially non-smooth problems. And the reason smoothness as a concept is very important in mathematics and in optimization is if you, in the simplest form, imagine the graph of a function that you might be dealing with in elementary calculus. One of the things we notice about the graphs of functions in that context is they have a smooth curve-like shape to them. They don't have sharp points and they don't necessarily have discontinuities. Whenever you have a sharp point, which is a lack of smoothness, you tend to lose some capacity to measure aspects of rates of change or the calculus that underlies the function that you're studying. So I was interested in functions that had sharp points and discontinuities and having to study their behaviour, trying to find optimal solutions, maxima and minima for those sorts of functions in a non-smooth environment. So there's a very large body of work in mathematics that studies these sorts of phenomena and then tries to develop conditions which would characterise optimality. So I spent many happy years hunting for very interesting solutions to some very pathological problems in mathematics. Well, of course, mathematics is a discipline where research, particularly in the pure form of mathematics, and although I said optimization is an applied discipline, which it is an applied discipline, it's actually, in the sense in which I pursued research, it is much more of a pure mathematical discipline. It brings some of the pure analytical tools of mathematics and applies them to mathematical problems that have been formulated, potentially from some real-world application, but a mathematician, in a sense, likes to push the real world to one side and operate in a conceptual framework, which is very much different, usually in multiple dimensions or high dimensions and so on. So it sort of escapes the reality and focuses on a problem, and then we apply pure mathematical reasoning to that. So research in mathematics is actually very much an inquiry discipline. You pursue, you take existing results and either try and apply them in new or innovative ways to new mathematical models. You try and remove some of the constraints that apply to a particular set of problems and say, well, can I actually still generate a solution here that might be computationally significant? Because one of the aims in my area of mathematics, of course, is not just to formulate conditions that characterize optimality, but to be able to then compute in some way. So to be able to set up a piece of software that could take the input parameters of the problem and actually use these conditions of optimality to generate a solution, and then you could apply that in the real world context. So computational aspects are always in the back of our mind. So removing barriers so that we can broaden the class of problem that we can study, to test hypotheses about the systems we're looking at. And non-smoothness is a great example of this. For much of the sort of the 19th and particularly the 20th century, optimization emerged as an important discipline essentially post the Second World War, where operations research began to emerge as an area of studying some very important real-world problems, logistical problems, scheduling problems, all sorts of very complex problems where we could quite easily model the systems, but very difficult to generate solutions and to know you're at the optimal solution to the problem. And you can imagine if you're dealing with airline scheduling, then it's very important to model the system very carefully, but to generate a solution, because that could minimize delays and maximize profit for airlines and so on. So it emerged in that post Second World War period. It was a very important tool developed at the time of the Second World War, because they were dealing with post Second World War. They were dealing with the period in which Berlin was cut off in that Cold War period, and they were needing to schedule flights in and out of Berlin, and they needed some scheduling tools to do that. So OR, operational research, sort of emerged in that context. So one of the interesting things about that system is it had a lot of constraints on it, because it was simplified so it could be solved. In the last 50 or 60 years, mathematicians have been exploring ways to remove those constraints, to have more and more general problems to solve and to generate new conditions to compute solutions and to broaden the class of problem that we could solve in the real world. Nowadays, with computational power, you can crack a lot of problems just by heuristic algorithms. Just keep trying and trying and trying, you'll generate solutions. Whether you know you're at an optimal solution or not is always the test. How can you guarantee? And mathematicians spend a lot of time finding ways to test a solution for optimality. So you might be, or even to test a solution for near optimality. So one of the interesting things to do in mathematics is to say, well, this may not be the optimal solution, but we've got to it, and we're within a tolerance of where the optimum might be. So this is good enough, and can we develop a set of tools to do that? So yeah, computational power had something to do with it. As computers became more powerful, it meant we could begin to deal with much more complex problems. For me, it was actually quite a solitary pursuit, and I think it is for a lot of PhD students quite a solitary pursuit. I mean, I spent a lot of time immersed in the literature. In my day, when things weren't online when a new publication of a critical journal came out. I was, sitting on the floor in the Baillieu Library at the University of Melbourne just reading for a while, photocopying things, yes, but also just reading things through that related to my area of interest, and soaking all of that up and spending time with other researchers working in my field. I mean, in mathematics, you can be isolated even in a discipline context, but you can be working with people on similar sorts of problems, so you can engage with them about what they're doing, attending a lot of seminars. I think mathematics lends itself to really interesting things going on. You don't have a deep understanding of them, they're outside of your sub-discipline. Mathematics, like so many areas of pursuit nowadays, is becoming so specialised. People get very deep in a very narrow part of the mathematical spectrum, but to still have that broad interest in what's happening in the broader mathematical discipline. So attending those sorts of seminars, getting to conferences as much as I could, and to, as a young student, PhD student, it was always a bit daunting to go up to after a lecture to a well-known mathematician to explore my particular question that I wanted to put to that particular individual, and hope that he or she had a bit of time to spare to, which they generally did, and they generally, most researchers do spend time with young academics, young researchers who are pursuing an interest. So yeah, it can be a solitary pursuit, and I think you need to find those other avenues to connect. And certainly for me, it was writing down a lot of ideas and testing them out and talking to colleagues. And as a mathematician, when I was writing up my thesis, of course, I became deeply interested in mathematical typesetting languages. This is an aside in a sense, but mathematics is such an elegant and beautiful discipline that when we present our results as mathematicians, we're always looking for the most elegant way to produce them on the written page. And as you're published in my day, in the 80s and the 90s, in the early part of my career, you'd get back the page proofs from a journal, and you'd be correcting the page proofs, and you'd be trying to ensure that they captured the beauty of a formula or of an expression, which is full of the Greek language, which, like mathematicians are using Greek symbols and many other symbols to create complex formulae. But when you start to write your thesis, you begin to engage in, well, how can I produce this in a way that represents the elegance that I'm trying to generate? And mathematical typesetting languages like TeX and LaTeX and those other languages were just emerging. It was an extraordinary time for mathematical typesetting. So it's a strange, quirky thing, but deeply interesting to those of us who want to typeset beautifully. Look, I'm not sure that there are any more challenges researching in mathematics than there are in any discipline at the highest levels. You are interested in pursuing ideas to see where they take you. You're interested in being ahead of your discipline, so to be on top of the literature, to be deeply engaged with researchers around the world. In fact, one of the best parts of my mathematical research career occurred when I was just post my PhD, and I was pursuing some ideas in an area of what was called quasi-differentiability. It's a type of non-smoothness I was looking at, and there were a group of Russian mathematicians at the time who were leading the way. They had produced some really interesting results on this type of non-smoothness, and I was interested in understanding aspects of it. So I wrote a letter to one of them, as you did in those days. You actually wrote a letter and you posted the letter to Vladimir Demyanov in St. Petersburg. And many, many weeks later, I received a wonderful response from his collaborator, Alex Rubinov. And Rubinov and Demyanov had written some great work over a long period of time in non-smooth analysis. And Alex wrote back to me a very long and detailed handwritten letter in response to my questions, and it set up what became for him, because he passed away a few years ago, our lifelong collaboration together. We wrote many, many papers together after that. But that first series of papers were very complex, because he was for a while in Russia, then he was in Azerbaijan. He fled Azerbaijan as a Russian Jew in the early 90s. Ended up in Turkey for a while. I hunted him down to find him and ended up then in Israel. And I was able to bring him to Australia, and we worked together for about a decade and did some wonderful work together. But it's that beautiful exchange where you literally would wait weeks and weeks and weeks to hear back from a colleague when they had no access. It was the early days of email, but no access to it at the time. So I miss some of that actually, in that context of anticipating great pieces of mathematics to wander back across the world. I think one of the most important things that we can impress upon our students is the importance of collaborating. Engaging, first of all, because collaboration is a richer form of engagement. It's where you really are having a dialogue and you're developing ideas together. I think in the biomedical sciences and the biological sciences, team-based research is the norm. Even though people have individual topics, researchers often bring their students together and they have rich laboratory discussions about each other's work and contribute to each other's work. I think it's a great model. It doesn't necessarily apply in other forms of, or other disciplines or other discipline contexts. So you need to find your way to engage, and I think we need to encourage our students to find their way to engage. There's a responsibility on supervisors to help them, to make those connections. My supervisor would often help me when I was discussing an idea from a particular researcher somewhere in the world about how to connect with that person, and he may have had a connection at some time in his research career, so we exploited that. We got in touch and we talked about how we could work together. Another example of that in my case, I wrote a number of papers with my supervisor. He was always very generous of spirit in the way in which we published together. I can remember the moment at which Craven and Glover became Glover and Craven. This was an important moment in our relationship. It was post-PhD, and he comfortably felt that my contribution then warranted first authorship, so we moved together in that way. But I wrote a paper with him which was pointing out an error in the paper of another researcher, very, very famous researcher in Norway, and we published this paper pointing out a very significant error in some analysis that the other author had done. But it set up a dialogue that went on to be a great collaboration with the Norwegian researcher, and we published together then for a number of years. And I think it just highlights that there is a little trepidation and can be a little fear of making those connections, but to be honest, they're the lifeblood of research. I think probably true in every discipline, and certainly true in the mathematical sciences. So yeah, I think it's so critical. First of all, start writing early and often. I know that my supervisor said to me, I met with him on a weekly basis in the early stages of candidature because he was asking me to read things and come back. And I got in the habit of writing things down, whether it was trying to understand a complex proof that was eluding me, or some ideas I had to extend a piece of work, but I'd write it down and hand it to him and we would talk about it. And that led to early publication. So in my discipline, I think it's very, very important to publish during candidacy. This is not true in many other disciplines, and often isn't the case in the humanities, for example. But it is, I think, very important in many of the sciences that we encourage our researchers, our young researchers, our PhD students, to take their work and to take it into the peer review context, a conference paper. There's nothing better when you submit a thesis than to know you've had 3 peer-reviewed publications that are embedded in this thesis, and you know it has substance. You know that you've responded to that peer review and you've improved your work as a result of it. So write early and often, I think, is absolutely critical. Where the context is right, to attempt to publish your work, and I think it's so important to get to conferences, whether they're local seminars, whether they're national conferences, or whether they're international conferences. Encourage our students to get out and meet their fellow researchers wherever they may find them. And finally, to avoid the isolation, within the context of the research group or the school or the institute or the centre that they're a part of, to participate as a PhD student. I think students are welcomed into those environments and they should feel confident to participate. It may not always be directly related to their work, but that's, in a sense, secondary to actually soaking up the research activity of others and the ideas that others are generating. So there's some of my pieces of advice.